Chapter 3 is a discussion of the whole number system. So 3.1 that we just completed talked about different numeration systems. You'll notice that all the types of numerals that we were using either had or didn't have a zero, but then they had only positive values after that. We didn't do anything with fractions or decimals, anything like that. Chapter 3 is working with exclusively whole numbers. And in section 3.2, we're going to be working with addition. So we're going to start with a definition of addition. So addition of whole numbers is defined as follows. Let A and B be two disjoint finite sets. Disjoint means they don't overlap, right? So these are circles that are non-overlapping from a Venn diagram perspective. If the number of items in set A is little a and the number of items in set B is little b, if you add A and B together, you will actually get the number of items in the union of the two sets. The numbers A and B are called the addends, and A plus B is called the sum. There is a condition here that I want to sort of draw your attention to, and the condition is that the sets A and B have to be disjoint. So our first example is going to deal with just that. It says to give an example to show why, in the definition, the sets have to be disjoint. So we're going to create sets that are not disjoint. I keep using the wrong keystroke. Two sets that are not disjoint, and show how the definition would fail if I didn't have that condition met. So of course, disjoint means they're completely disconnected. They do not overlap. So if I'm wanting to create them so that they don't do that, I do need them to overlap. Now there's nothing special about what we create, so I'm going to use numbers like I have in the past. And we're just going to write a few of them down. I'm going to go with the first 4 digits. And then I want something of that list to be present in the list for B. So we'll just pick up with the 3 and the 4. And we'll do 5, 6, 7. Okay, there's nothing special about these values. They simply have to overlap. So what we're going to do first is we're going to find the union of A and B. So you guys have done this before. Union means we get everything, right? It's the family picture. So what numbers are in my union?
1, 2, 3, 4, 5, 6, 7.
Yep. All 7 of them. And then we're going to do counting. So we're going to find the number of items in set B. So how many items are, set A. How many items are there in set A? 4. And we're going to do the number of items in set B. How many are there? 5. And we're going to do the number of items in the union. What was that? 7. And you'll clearly notice that if I add these two together, I get, hang on, let me put it this way. If I add these two together, I get 9, and 9 does not equal 7. Right? Why? Well, because I counted the 3 and the 4 twice. Right? And we talked about this back when we talked about Venn diagrams, but that's actually what's happening here is that I have to have disjoint sets for this description to make any sense. So what we're going to be doing a lot in, especially sections 3.2 and 3.3, is modeling. So these are very basic level kinds of things that you would see early childhood stuff. All right, so those of you who are early childhood and you've been like, Venn diagrams are not going to be good for my 5-year-olds. This is probably good for your 5-year-olds. All right, so set models are typically used for things that are whole objects. For example, if Liz has 3 blue crayons and 2 red crayons and she combines all the crayons together, how many crayons does she have? So it doesn't matter if the crayon's brand new or if it's one of those, that's flattened on the end because they've been used so much, we still count it as a whole crayon. All right? So if we were working with Liz on this and we were talking about her crayons, we might actually, we would probably actually have physical crayons to do this. But we're going to draw a picture representation since we're working since I'm working on a screen anyway. And so we had, let's see, 3 blue crayons. Let me do blue first. So I'm going to draw 3 blue crayons. And they don't even matter how big they are or anything. Size is irrelevant. And then I have 2 red crayons. And the question is, how many crayons do I have total? and young enough, the child would actually just count them, right, from start to finish, and they would find out that they have 5 crayons. So this is a set model. We count numbers of actual objects to come to our solution. Our next model is the number line or a measurement model. You'll hear them called both. This is typically used for objects that can be partitioned. So we're still going to be working with whole numbers, but we're working with things that do have a fractional value that makes sense. So Joe has 4 feet of wood, right? So could he have 1.5 feet? Yes, he could. That's why this is a number line model or a measurement model, because it makes sense to divide that into pieces and to count it like that. We're still working with whole numbers. So Joe has 4 feet of wood and 3 feet of aluminum. How many feet of building material does Joe have? So the reason it's called a number line or a measurement model is because we can put it, in fact, on a number line. So we're going to start at 0. And that's a bad 0. I'm going to measure off 1 foot at a time. 1, 2, 3. And it says, oh, he had 4. I don't have enough space. Let me actually change my numbers real quick. I'll do this as 1, 2, 3, 4. So he has 4 feet of 4 feet of wood, and then 3 feet of aluminum. So here's my 4 feet, and I can actually draw in, visually speaking, my pieces of wood. I'll draw them in brown. So here's 1 foot, 2 foot, 3 foot, and 4 foot. I have 4 feet of wood. You can almost think of it like planks of wood, but that's not necessarily broken apart. And then I have 3 feet of aluminum. So I will take the same idea and I'll mark out 1 foot, 2 foot, and 3 feet of the aluminum. And I have 5, 6, and 7 then. So how many feet of building material does Joe have? He has 7 feet. So in this model, we're actually not counting pieces like we were before. We're actually counting lengths. All right, so some other things to do with whole numbers. When we talk about whole numbers, we have the concept show up of less than. We also have the concept of greater than. We're only defining one of them. Your book does. It actually talks about the greater than in the homework part of it, so you'll see that show up there. Less than means that if you have any whole numbers A and B, A is less than B, written as you've seen before with the less than symbol, if and only if there exists a natural number K such that A plus K is equal to B. So this is actually not probably how you think about this working, but it is what actually happens every time. So why is 5 less than 7? Well, because there is some number I can put right here that makes them equal, and it's a positive number. And in particular, that number for this would be 2. So there's always some number I can add to the smaller value so that the two sides are equal. That's what it means for something to be less than. So this definition is using addition to describe less than. We're going to write a very similar statement on example number 2, but instead of using addition to describe less than, we're going to use subtraction. So the only thing that's really going to change in this definition is what I circled in red, and in particular a little bit more broadly, this equation won't be the same. Everything else will be. So you get a lot of this for free, you just get to write it down. For any whole numbers A and B, A is less than B. Hang on, these words first. A is less than B. Written, A less than B. If and only if there exists a natural number K, Such that what? What's going to have to happen in order to create a relationship of equality between A and B?
B minus K equals A.
Yeah, I didn't have to write such that yet. So such that, and I'm going to keep the order the same. So A is equal to B minus K. If you switch the order, it doesn't matter. But yeah, the A and the B stay on the separate sides of the equation. And instead of adding K to A, I'm going to subtract K from B. Right? So it's the same description, but using subtraction at the very end instead of addition. All right, so the next thing we're going to be looking at is properties of whole numbers. We have 4 basic properties of whole numbers for addition. The first one is called the closure property, and it's the most difficult one for students usually to grasp. It says if A and B are whole numbers, then A plus B is a whole number. It's one of those things that you know to be true, right? If I add 2 whole numbers together in, first grade, I'm not all of a sudden going to end up with a -7. Right? I'm not going to end up with a 4/3. I'm not going to end up with anything like that. I'm just going to end up with another whole number. Closure has a little bit more to do, so we like that property and we think it just seems sort of obvious. But the reason I mention it this way is because it's not quite so obvious. It's very special to addition and whole numbers. For example, let's say you were looking at just like fractions, not like fractions that can be reduced to whole numbers, but just fractions. This wouldn't hold. 3/4 plus 1/4 is not another fraction, right? It actually becomes a whole number. Not exactly what we thought, right? It doesn't work for every operation. Consider subtraction. We'll do subtraction in section 3.3. But if we did subtraction, this wouldn't work, right? So 3 plus 5 is 8, and 8 is a whole number. But what's 3 minus 5? -2. That's not a whole number. So one of the ways that I've heard this described before, if it helps you for a visual, is imagine we have our door of our classroom, all right? And everything, all the numbers, in this case whole numbers, are floating around in the ceiling of our classroom. Okay, there's all these numbers that are just floating, right? The set is closed. You have to have an operation. We're using addition. The set is closed if I can take 2 numbers that are inside my room and I add them together and I get another number inside my room. So my example where I used the operation of subtraction and I took 2 numbers inside the room, whole numbers, and I did 3 minus 5, and 3 minus 5 ended up being negative. It's not in the room. I don't have any negative numbers in the room. I only have positives. So the door would have to be opened, right? I no longer have a closed set. So we'll talk a little bit more about closure in a general sense in your homework for this section as well, because it's not just whole numbers and addition. There are other sets that have the property that's closure as well, and you'll explore that a little bit more. A couple other properties. The next 3 are ones that are more straightforward, easier for us to process with, I think. The commutative property says if A and B are whole numbers, then A plus B is equal to B plus A. All right, 5 plus 3 is 3 plus 5. It's the reason when the children are learning addition facts, it's true for multiplication, but addition facts in school, that once they get to the 9s, it's pretty easy because they've already added 9 to everything else. The only new fact that they need is 9 plus 9, right? Because they did 9 plus 3 when they did the 3's tables. Okay, so that commutative property is a very helpful one. The associative property. The associative property talks about grouping things together. So in particular, if I have A plus B grouped together in a set of parentheses and then I add C on, because it's addition between each piece of this, the grouping symbols are irrelevant. I can group whatever I'd like. So instead of grouping A and B, I could group B and C. And actually, if you combine the commutative property with the associative property, you could also group A and C together first instead. Now again, why is that useful? Why does it matter? Well, sometimes it's easier to add 2 numbers together first and then add the third one than to go in a different order, right? Because it might add to something like 10. Adding to 10 is really nice. If you know that 7 plus 3 is 10, that's very handy. If you know there's a 7 and a 3 in that list, you might choose to add those together first. And the last one's the identity property. The identity property says there's a unique whole number, 0, 0 is called the additive identity. And the reason it measures up, that it sets the criteria, is that the criteria is that a plus 0 is equal to 0 plus a is equal to a. So when I add it to another value, it never changes that other value. And once again, you might feel like, well, that's sort of worthless, but I think you guys know it's not, because eventually these are the kinds of things that we do to equations to get them to balance, right? You add a number to one side and another side at the same time. It's kind of a balancing thing. You've really added 0 to the whole equation. So we see that property at play when we get to algebra. So what we're going to do next is we're going to look at a set of, I think it's just 4, of 4 different expansions or equations and decide which property is being portrayed. Okay? So I'd like for you to take just, 30 seconds. Write down next to each one of them what property that you think is being displayed. And once you have your 4 that you expect them to be, that you think that they are, turn to somebody close to you and just check and see if you thought the same things. And if not, talk about why they differ and what maybe is going on in your thoughts. So check with someone nearby. Okay, so what did you decide the first one was? What property is that? That's the commutative property. So commutative property can be identified because something changes locations. How about the second one? That's the additive identity, and it is really important, if you didn't write it, that you write the word additive and not just identity. And the reason is because we will have a multiplicative identity later, and it's not 0. So we need the additive identity property. How about the third one, C?
Commutative.
It's commutative as well. It might have tripped you up because you saw parentheses. A lot of times it will. But what's actually changing is the order of the numbers in the parentheses, not what the parentheses is surrounding, right? So this is another example of the commutative property. How about the last one? That's the associative. The parentheses here are around 5 and 3, but over here they shift and they're around 3 and 2. So this is the associative property. Any questions on those? Okay, I want to do one more block of information in this section and then we'll pause because I don't want to break the next part apart. There are, I think it's 4 listed, 4 different basic addition strategies. And you've probably, 3 different basic addition strategies, and you may have seen them used. And I will tell you, having a child just come through first grade, I've seen some of these things used in ways that they were not used 12 years ago when my first daughter was in first grade. They just are used differently. So these things do change. Counting on is one of our addition strategies. When we have a counting on addition, what we're doing is we're starting with one value and we're counting up to the additional amount of the other value. right? So like when you have 5 plus 3, you don't have to have objects and start with the number 1, 2, 3, 4, 5. You simply start with the larger value, namely 5, and you count up 6, 7, 8. Right? You count up the other 3. So that's a counting up strategy. That one's very common, and it's very old. We've used that one forever. Doubles is the one that I usually see people like, why would they teach them that? Doubles are actually very helpful. So they did doubles with my daughter when she was in kindergarten. That's what she learned before she learned plus, all her plus 0 facts or all her plus 1 facts. They learned doubles facts. 0 plus 0, 1 plus 1, 2 plus 2, 3 plus 3. That's what they learned first. So if a student knows the doubles facts, like 3 plus 3, okay, what that means is they can do things that are called near doubles. So when they have something like 3 plus 4, they can say, oh, look, that's a near double. I know 3 plus 3 is 6, so it's 1 more, so it's 7. And that's exactly how my daughter still thinks about her near doubles, is that she uses the doubles idea. So this is a new convention that we see used more frequently now than I've ever seen it before. And then the last one is one I mentioned in passing before. This is a method of adding to a value of 10 and then including leftovers. So I mentioned before that if you know your values that add to 10, well, right, 6 plus 4 is 10, 3 plus 7 is 10, 8 plus 2 is 10, 9 plus 1 is 10. You know the things that make 10. Sometimes it's easier to look at values than to break them apart. For example, 8 plus 6. Well, I know that 8 plus 2 is 10. So in essence, what I'm doing is I'm breaking the 6 apart into the 2 that makes it easy to add to 8 to get to 10, and then the other 4 that are left over. So 8 plus 2 is 10, plus my remaining 4 gives me 14. So that is a strategy called making tens. So we're going to talk about some actual algorithms, which means methods for doing addition next time, but these are some basic, simple strategies for us to think about first.